Flip a coin 10 times. 8 heads, 2 tails. How does a model know which parameters are best? Here are 3 candidate coins. One says fair, heads half the time. One says heads 80% of the time. One says heads is almost guaranteed. Which of these coins explains what we just saw? The 80% coin. It's not a guess, it's the coin whose story best matches the evidence. This is Chapter 9. Maximum likelihood. How machine learning learns from data. Welcome to Data Alchemist. 2 questions look almost identical, but they run in opposite directions. Probability fixes the parameter. If the coin is fair, how likely is this data? Likelihood fixes the data. We already saw 8 heads. Which value of P makes that outcome most believable? Same formula. Roles swapped. Probability treats parameters as fixed and asks about data. Likelihood treats the data as fixed and asks about parameters. With those roles clear, we can now build the likelihood function itself. 8 heads means P multiplied by itself 8 times. 2 tails means 1 minus P multiplied by itself twice. L of P equals P to the 8th times 1 minus P squared. Plot this across every possible value of P, and a curve appears, low at the edges, rising toward a peak. The peak sits at P equals 0.8. That's not a coincidence. It's the parameter that maximizes the likelihood, the argmax of L of P. Products do not scale, so we use logs. Real datasets have far more than 10 points. Multiply hundreds of small probabilities together, and the product vanishes towards 0, underflow. So we take the log. Log turns multiplication into addition. Each tiny probability becomes a log probability, and the product becomes a sum, the log likelihood. Because log always increases, the P that maximizes the likelihood also maximizes the log likelihood. Nothing about the answer changes, only the arithmetic gets safer. Flip the sign and the objective becomes a loss. Machine learning frameworks are built to minimize loss, not maximize anything. So flip the sign. Maximizing log likelihood becomes minimizing negative log likelihood. Picture that negative log likelihood as a bowl-shaped landscape. Training a model means walking downhill on this bowl step by step until you reach the bottom. The parameters that made the data most probable. That descent is gradient descent. The bowl is the loss. The bottom is your answer. For binary classification, this negative log likelihood has a familiar name, cross-entropy. Take a spam classifier, 4 emails, 4 true labels, 4 predicted probabilities for whatever the correct label happened to be. Multiply those correct label probabilities together and you get the likelihood of the whole label dataset. A good classifier keeps that product high. For a single binary label, the probability model is Bernoulli, p to the I times 1 minus p to the 1 minus y. Take the negative log of that and it becomes binary cross-entropy minus y log p minus 1 minus y log 1 minus p. If the true label is 1, the loss is minus log p. If it's 0, the loss is minus log 1 minus p. Confidently wrong costs a lot. Confidently right costs almost nothing. This is exactly why logistic regression and neural classifiers train on cross-entropy. Regression follows the same principle, but with a different probability model for the errors. Now, regression. Assume each observed y is a prediction plus Gaussian noise. Every point sits near a line, off by some random residual. The likelihood of the whole dataset depends on how large those residuals are, weighted by a Gaussian bell curve. Maximize that Gaussian likelihood and the algebra collapses into something familiar. Minimize the average squared residual, mean squared error. MSE was never an arbitrary engineering choice. It's what falls out of assuming your errors are Gaussian. Different error stories produce different losses. Different assumptions about noise produce different loss functions. Mean squared error comes from Gaussian noise. Mean absolute error comes from Laplace distributed noise. Cross-entropy comes from a Bernoulli or categorical model, and negative log likelihood is the general purpose loss behind any probabilistic model, including large language models predicting the next token. Every loss function is a hidden statistical assumption wearing an engineering name. Put all of these examples together and the full path from data to training becomes visible. Data becomes likelihood, then log likelihood, then negative log likelihood, the loss we minimize to train. Maximizing likelihood and minimizing loss are the same operation, seen from two directions. A model doesn't learn by magic. It learns by making the data it saw as probable as possible. In Chapter 10, we move from choosing one best explanation to updating what we believe as evidence arrives. Bayesian machine learning, updating beliefs with data. Thank you for watching. Subscribe and stay curious. Keep following the statistics behind machine learning.